Good morning, fellow engineers. This is Jaira from MIDAS IT Philippines. The webinar will take about 75 to 90 minutes. You can use the question tab if you have any concern or questions, and our staff and me will try our best to answer them. Today, we will be talking about Super T Girder Bridge, how to model, analyze, and design this using MIDAS Civil. You will find attachments in the attachment tab of GoToWebinar. You can use it as a reference as we go on with the discussion. In other developed countries such as New Zealand and Australia, Super T has become the preferred section for bridge spans 18 to 35 meters. So this is because they are avoiding girders with closed voids due to casting issues related to accurate restraints of void formers. And also they have a difficulty of verifying casting and compaction. Here are the current Australian practice. So as you can see, for spans 18 to 35 meters, they are using Super T and tear-off beams. So in AS code, they have various modifications of Super T girder bridges, Super T girders. So they have varying depths from 750 mm up to 1,800 mm with the following span. So for 1,500 mm, for example, the span ranges would be 30 to 35 meters. All throughout this discussion, we would be referring to AS5100 year 2017. So we will be mostly referring to AS5100.2 and AS5100.5, referring to the loads and to the concrete design. So here are the data that is available to us. We have 3-span bridge with 32, 35, and 32 meter spans. And then we also know the height of the columns. So for today, we will only be modeling the 2 interior columns or interior piers. And then for the section, we have 6 Super T girders. And we also have precast concrete barrier. Here is the dimension that corresponds to the moving load beams, as well as the shoulder and the location of the precast concrete barriers. It is essential to know this information before moving forward with the modeling so that we can provide enough information for the model to conduct its analysis. Here are the material properties that we would be using for our model. So for the girder, we have grade 50 concrete, and for the slab and the substructure, we'll be using grade 40. And then we would be using the function found in AS 5100.5 for concrete design of Australian standard for creep and shrinkage as well as for compressive strength. And then for our pre-stressing steel or tendons, we will be using the standard from AS or New Zealand Standard 4672.1 with 1870 minimum strength, and then we'll have a yield strength of 1569 MPa, and the strand diameter that we will use is 12.7 millimeters, and we'll have a jacking or pre-stressing force of 1396 MPa. So here are the tables that can be found in the Australian standard for concrete, the creep and shrinkage, as well as the compressive strength, and then the properties of tendons according to AS 5100. So we will be using the wire ordinary strand 12.7 with 1870 MPa minimum breaking strength according to AS 5100. So I will be starting modeling from scratch, but later on we would get some information from a predefined model. So let's create a new model. So in the properties tab, you can define here the material properties that is based on AS5100. So first for the concrete, Let's scroll it down and then you can see here the AS17RC for the standard. Then here are the options. So we'll be using C50. Then you can verify the values of the properties here. Click on apply. Then C40 as well. Click on apply. And then we will be using steel type of design for the tendons. For the tendons, we have in the lowest part the AS New Zealand Standard 4672.1. Then under that, we have a database for 1870. So click on OK. So we already have our material properties. Then for the section properties, let's go to the other tab. You can add section property here. Then for Super T standards, MIDAS has already embedded the standard shapes of Australia here under PSE tab. Then click on PSE value, section data from database. Then choose the AS code. Then as you can see, we have T1 up to T5. So here are the dimensions of type 1, type T1, type T2, T3, T4, and then T5. So we will be using T4, the one with depth of 1.5 meters. So let's get the one with T4. Then click on OK. So we have one T4. Then we need to define the parameters for design. So we need to define T1 or the thickness of the top flange that it will use. So in this case, it would be here. Then you need to also define T2, the thickness of the bottom flange, the width, and then the effective height. So for the thickness, the top flange, let's put 75 mm. And then thickness of the bottom flange, 260 mm. Then the width, 0.58. And then for the effective height, 1.3333 meters. Then for the thickness of torsion, we need to input the thickness of our web here, 120. And then for the position of Z1, Z2, and then Z3, we also need to define it. For Z1, it is the termination of the top flange and the web. Then for Z2, it's centroid, so it is automatically defined. Then Z3 is the termination of the bottom flange and the web. Then for other section properties, we can just click on auto for it to auto-calculate. And click on apply. Then after this, we also need to define a closed super T section. So we can define it by clicking the define coordinates. So define coordinates, you can change it by changing the coordinates of X and Y. Then you can also change it by deleting some of the points. So now we will be deleting points 11 up to point 19. So if you delete those, you will have a closed super T section. So click on OK. And let's rename it into close T4. Then click on OK. So now we have data for T4 and then the closed T4. We will be adding the composite section for this PSC. So add another one, then go to the composite tab. In this case, we'll need to define composite PSC since T4 and closed T4 is defined under PSC tab. So for BC, we need to define the slab width, 0.96, then thickness of the slab, which would be 0.18. So 180 mm. It is also stated in AS5100 regarding the slab thickness and the slab width. Then we will be importing the PSC sections that we have defined before. So we have T4. Then we will need to select the material for the slab and the girder. So this is for the composite section to be analyzed as composite and non-composite. So let's get it from AS17 database for slab C40, then AS17 as well for the girder C50. And let's click on OK. And then the modular ratio would be automatically computed. Then let's change the offset into center top. Click OK. Then don't forget the name of the section. So this is composite T4. Apply. Then we would do the same for the closed section of T4. So closed composite for T4. Then click on apply. Then for the other section properties like for the column, pier cap, and the diaphragm, we'll be modifying it here in the database or user tab. So first the column. Let's define the column. So So we need to have solid round, and then the diameter of the column, click on apply, is 1.2 meter. Then let's also define the pier cap or the coping beam. So coping beam is solid rectangle, also in user defined format. Let's change this into center top and click on OK, apply, and then for the diaphragm as well. So solid rectangle again. And then diaphragm. So 1 meter by 0.6. And click on OK. So now that we have material and then section properties, the other properties that we need to define are the time-dependent properties, which as I said before is based on the AS5100.5 or the concrete design for the Australian code. So let's click on the creep and shrinkage for us to make a function. Let's click on add. Then under code, let's just look for the AS5100 here. AS5100.5 2017. So yeah, let's not forget to save our models. So let's save it as model 1. So the basic data that we need for modifying the time-dependent properties for our concrete materials would be the compressive strength of concrete at the age of 28 days. So for C50, we have 50 MPa. Then we need to also define the exposure environment. So as of now, since this is based on the Australian standard, we only have four classifications: arid, interior, temperate inland, and then top tropical or near coastal. So since this is based on the engineer's decision, depending on the location of the bridge, can define arid or tropical, or if it will be in the Philippines. Then for the hypothetical thickness, we have here the formula. So we can input here 1 first because this will be automatically computed after the time dependent factors are inputted. And then for the drying basic shrinkage strain, it's only limited to 3 as of now: Sydney, Melbourne, and then let's just put elsewhere. And then the age of concrete at the beginning of shrinkage could be 3 days. So here's the graph, which is also the same with the graph that can be found in the AS code. So this is the graph for the creep, and then this is the graph for the shrinkage, which is also found in AS5100.5. So you can see it creep and then for the creep for the shrinkage. And then we'll do the same for the C40. And after that, let's also create another function for the compressive strength. So C50, Australia. And then input the compressive strength. And here's the graph. Then click on OK. Then add another one for C40. And then we have, for review, we already have the material properties, time-dependent properties, and then the section properties. We also need to have the tendon properties if you want to move on with the wizard. So we will be using wizard later on. For the, it's under the load tab, under temperature or pre-stress loads. Then we could define the tendon properties here. So tendon property, then let's add one. Let's make our tendons with one tendon property as at first. Then this would be pre-tension. So super T girders are usually pre-stressed with pre-stressed pre-tension girders. Then for material, we'll use 1870S. Then so again, strand diameter of 12.7 mm, and the number of strands, let's make it 3. And then strand diameter is automatically computed here. Then for the relaxation coefficient, if it's according to AS5100, you need to input the RB. So for RB, under AS5100, this is the formula. So it's the basic relaxation of the tendon after 1000 hours at 20 degrees Celsius. So after we compute it, or after we get it from the NCC 4672.1 code, we can input the value here. So I'll be inputting 5%. And then I kept the default values of the characteristic value of strength and the yield strength. And click on OK. Then close. After we have defined all the properties that we need, material properties, time-dependent properties, section properties, and tendon properties, we can now proceed with the modeling of our structure. So there are different ways on how to model your structure. First, you can model it using the wizard, the pre-stress composite bridge wizard. You can also model it by importing the XF file into your models, and you can also model it using the modeling functions of MIDAS you will found in the Node and Elements tab. For us, the easiest way would be to model it using the structure wizard, the pre-stress composite bridge wizard. So the pre-stress or the pre or post-tension composite girder bridge wizard has 5 tabs for layout, section, tendon, load, and then the construction stage. So in using your girder bridge wizards, you can open a predefined file, and you can also save your created wizard files as a reference for future use. So we can define here in the layout tab the girder type. So we have two girder type, precast girder type and splice girder type. So precast girder type, this is where girders are fabricated off-site and are erected span by span. While the splice girder type, girder is fabricated in multiple pieces and then are connected at the splice locations. So for now, we'll be using precast girder tab since this will be a straight bridge. Then you can use different modeling types. So we have three here: all frame, deck as plate, girder as frame, and then all frame, non-composite. So the first option of all frame, this one considers the composite action of the bridge. Then all frame, non-composite, considers the different parts of the bridge as separate from one another. So we will be using all frame so that the slab and the girder will help in resisting the loads on top of it. And then for the span information, just input 32, 35, and then 32. And then for the deck width, so input 17.76. Then layout offset is 0, as well as the support skew angle would be 0 since this will be a straight bridge. And then for the spacing of A, let's input 0.50. So this will be the gap between the two girders when non-composite action of the girder are being considered. And then for the spacing B, 0.25 is the gap between the support and the edge of the girder. Then in the latest version, you have the option to check it either as continuous or non-continuous girder. Then if your bridge has some ridges or circular in layout form, you can check on the radius and then input the curve data or coordinate data of your bridge here. Then you can also input the substructure data of your bridge here. So let's check on the with substructure. Then here's the guide. So for the abutment, you can choose if the support is fixed elastic link or the same as pier. So we'll be having the abutment as fixed. And then for the pier, let's use the elastic link. Then for the x direction, for the stiffness of x direction, let's input 1.5 kilonewton per meter raised to 6. And then for the ky, or stiffness in y direction, 3000. Then stiffness in z direction, 3000 as well. Then the elastic link length, let's reduce it to 2.3 meters. Then for the material of the pier, let's input C40 for the substructure, then the section of the pier cap, the one we defined before. Then let's set the pier cap same with the deck width. And then for the column, then the height of the column, set this as 9. But if you want to define different column heights for every pier, you can check on advanced and then modify your pier height here. So if you input spacing, it will automatically change the arrangement of your columns accordingly. So if you put one spacing, it will input two columns. So again, here are the data for the layout tab. Then next for the section tab, let's input the deck thickness. So 180 mm, 0.18. Then material for the deck or the slab C40, girder is C50, and then diaphragm as well is C50. And then input the number of girders. So here is how the syntax of the wizard goes on. So from the layout, from the reference line, going to the left is, going to the right is positive, then going to the left is negative. So input here, negative 7.4, negative 1.48, and 1.48, and then 7.4. Then if you haven't yet defined the diaphragm section, you can define it by clicking the Define Diaphragm Section button. And then you can click on Advanced if you want to um, delete or not include the end support or peer support or the intermediate diaphragm. So I will not be including the end supports. And then here are the numbers of intermediate diaphragm per span. Then the spacing for the transverse deck element, I will set it as 1 meter. And then for the girder information for each tab, so let's input two divisions so we can add the closed tab. So for 0 to 2.0 to 2 meters, let's input the uh, closed super T. And then from 2 meters up to 31.925, let's input the super T with the void. And then for the second span, let's set it as super T girders without the closed section. And then for the third span, let's also apply the same, just like the span 1. So apply. And then from 0 up to, so for 29.925, set it as the super T with the void. And then for the last 2 meters, let's set it as the closed super T section. Then let's uncheck this one since we already have the transverse deck element per 1 meter. So let's now proceed to the next tab, which is the Tendon tab. So if you click on the guide for the Tendon tab, you can see here the different shapes for multiple span girder types. First, we have the harp one. So here are the tendons on the mm, on the elevation view of your bridge. Then for the harp 2, and then for the curve. So the curve shape is parabolic. So since we will be only using the straight shape, so here's the straight shape, the red drawings. Now we have a auto generation function for the tendon template, which can be used for the type 4 of super T, which we have used. So all you need to do in order to automatically generate the tendons for the super T with 1.5 meter depth, just click on the auto generation button, then select the tendon property, use ASS code, and then choose T4, then check on the initialize tendon template, and then click on OK. Then it will automatically input these tendons in your table. Then afterwards, you'll need to define the routing for each tendon. But for me, since I have the debonding data for the tendons, I defined it in the detailed section for the tendon. So if you click on detailed, you can see here that it has a name for every tendon. So for T1 on the first row, here are the tendons on T1 and then the number. So 1, 2, 3, 4, 5, and then 6. The reason that you cannot see the other tendons is because it has a debonding length. So here's the data for the debond length of your bridge. As you can see for the first row, row A, we have 2 debond length on 1 meter. So this is in mm. And then for the second row, we have 2 the bond length at 1 meter for the fourth and for the ninth tendons. And for the row C or the middle one, we have a the bond length on at 1.8 meters, 2 meters, and then 2.56 meters at the third, fourth, and fifth tendons as well as on the other side. And then for the fourth row, we have the bond length of 2 and 2.4 meters for the fourth and fifth tendons. So let's see how it is reflected in the detailed input for the tendon layout. So as you can see, T1 is at the bottom. So we have 8 tendons there with the first and the last that has the bonding. And then for the second row, we have the bonding on the fourth tendon as well as on the ninth tendon. And then for the third row, we have the bonding on the third, fourth, and then the fifth tendon as well as the eighth, ninth, and tenth tendons. So we put the bonding length here for every tendon, and then we put the jacking stress for each of the tendon here. So what you actually see here in the drawing is the extreme member of the span 1. So if you click on span 2, you can see here the tendons that are being pre-stressed on the second span and for the third span as well. So these are all first first elements of every span. So the next tab would be the load tab. So on the load tab, we have to define the distance for the barrier, the roadway width, and then the width of the median as well as the other roadway width and the other side's barrier. So if you don't have median, just like what we have in our model, in our data, you can input 0 there. And then as for the others, dimensions are indicated in the modeling statement given to you. So we have an option here if you want to divide the loads equally to all girder for DC before the composite and then DC after the composite. So I chose to divide it equally to all girder before the composite so that all the girders will have load. And then for the DC after composite, I decided that it should be on the specific girder only. So I did not check it. Then for the other loads value, so for self-weight, we only need to check it. So it is by default on the Z direction. And then for the weight of the wet concrete, we need to define the weight density and the thickness that should be loaded. So it should be 0.18. And then if you have formworks, you can also define the value of the loads here. And for median, we have median, so let's keep it checked. But we don't have, I mean, we have barrier, so we need to keep it checked. But for median strip, we don't have median here, so we need to uncheck it. And then for the wearing surface, here are the values of the weight density and the thickness of the wearing surface. And for the moving load case, in order to activate the live loads, we need first to define the moving load case. So check for the moving load code of Australia. Click on OK. Then check on the live loads. Define the traffic line lanes. So the traffic lanes are on the center of every wheels of the vehicle. So for the lane 1, The distance from the edge is 3.63. For the lean-to, the center of lean-to is on 7.13. Lean-3 is 10.63. Then D4 is 14.13. And for the vehicles, we also need to define it according to AS5100.2 for the loads. So we have standard for that. So it is divided into road traffic, pedestrian, rail traffic, heavy load platforms, and then for rating of vehicles, we will be using the road traffic. So we'll be using M1600. So M1600 is for the moving load traffic. Has a dynamic allowance of 30%. So here's the moving load traffic M1600, and here are the values that are stated in AS5100.2. We'll also be applying the stationary traffic load or S1600. So let's go back to the model. M1600 apply. And then S1600. Then S1600 doesn't have dynamic load allowance since it is not moving. So click on OK. If you already defined the two vehicles, then close this one. And then after that, we're done with the load tab. Let's go to the construction stage tab. So the construction stage guide shows that is being shown here. It has up to 8 construction stages. So whichever is applicable for our model, it automatically applies. So for example, CS1, where it erects the substructure and install false works if there are any. So we have that since we have substructure. And then CS2, the girder part. So our composite girder is divided into two parts, the girder and the slab part. So in CS2, girder parts are activated. And then for CS3-1, we have deck that is being considered as loads. So CS or construction stage 3-2, this is where the decks are considered as structural elements. And then for the fourth construction stage, after composite loads are activated already, like the bearing surfaces and the moving loads. And then for the fifth construction stage, long-term effect is considered. So this is where the time-dependent effect is being act onto our structure. So yeah, you can change the duration of each of the construction stage if you have verified it already. So after you fill out all of the details that are needed in the bridge wizard, you can save it. So you can save it and then use it again for other projects or if you have some revisions on your previous models. Then click on OK. Now that our model is completed by the bridge wizard, we can now inspect all the things that it has automatically generated. So you can see that on the end of the girder, it doesn't have diaphragm since we unchecked it on the section tab, but it have two divisions for the diaphragm, intermediate diaphragms. And then it already inputted two composite section for construction stage, the closed Super T and the Super T section. And then we can now inspect each of the construction stage that it automatically generated. So for example, for the stage 1, generated the substructure. Stage 2, it activated the girders. Stage 3-1, we already have self-weight, then the wet concrete load. And then for the stage 3-2, slabs are already activated. And then for the stage 4, the barrier and the wearing surface are activated as well. And for the stage 5, this is where the time-dependent materials are being acted upon. So we can only make changes on the base stage of our model. So we need to just um, modify some of the properties. Say for example, the material link of C50 and then C40. So in order for us to um, attribute the compressive strength, creep, and shrinkage to C50, we can use the material link here. So C50 and then which material should it be assigned, then add. Then we'll also do it for C40 as well. C40 and then add. Now it is already assigned. Then the next one would be to modify the moving load. So moving loads can be found in the load tab. So under load tab, moving load, then moving load cases. So let's add the moving load cases. So the program just auto-saved our model. So going back, we'll need to define moving load case, and then it could identify. You could identify it if it is a load case for permit vehicle or if you used moving load optimization. But if you used Girder Bridge Wizard, it did not optimize. So it can also modify if it's a general load model, fatigue load model, heavy load platform model, or rail traffic load model. So the load combination for these different moving loads will be different. So just identify it as general. And then here are the data for the accompanying lane factors. So these are also based on AS5100.2. So we need to define the subload cases. This is where we will combine the lanes and the vehicles together. So there are two loading effects, combined and independent. First, if you choose the independent, it will apply first the load before it gets the result. But if you choose to have the loading effect as combined, it will first combine the loads together and then give you the result based on that combined forces. We will could use the combined. Then add. So first for the M1600, we have 4 lanes, maximum number. Then click on OK. Then we would do the same with the stationary moving loads. Then click on OK. So now that the moving loads are already assigned, we can modify our composite sections for construction stage. So as you can see here, we have two composite sections, the Super T 1500 depth and the closed Super T. So first, we will modify the Super T. So we need to input the age. So I set it as 7 days for the first part, which is the girder. And then for the second part, the slab, 10 days. So let's just input first a value for age. Same thing with the closed super T. So this will avoid convergence errors or convergence warnings due to construction staging. Because if you did not define the age of your structures correctly, it can affect your model. So the strength of the girders will not be attained accordingly. So we can update all age. So it is successfully completed. You can see now that the age are updated. So we need also to modify the age of our structure in the construction staging. So it's on stage 2. So modify, and then here is where we will define it. So for the girder, so on the age 7, it should be activated already. Click on OK, then close. Then aside from that, we can also input the reinforcement so that we can use it for the design part. So for the reinforcement, it is under Properties tab, reinforcement. Then for the Composite T4, we can have a guideline so we can easily draw our reinforcements. So I'll be using input method B or using the coordinates. So I'll start from the guidelines to the end. Then input the number of the rebars, check on the edge bar, and then let's change the sizes here. So let me close this first, then go to the Tools tab, then modify the preferences for the sizes of the rebars. We can go to the Design or Load Code under Preferences, and then choose AS17. Click on OK. Let's go back again to the section manager, reinforcement. And then for the Composite T4, let's do it again. Then the number 18 with the edge bar. And say 16 mm. Then part 1 is the girder, part 2 is the slab. So it's should be on part 2. And click on apply. Then let's do the same for the shear reinforcement. So let's just input diagonal reinforcement. So for diagonal reinforcement, let's input pitch as 150 mm or 0.50, then angle 90. Then input a number of reinforcement for every meter. Then for torsional effects, let's input the same data. If you have preliminary design for this, you can also do that. But this is optional. You can just check your model first and then get the recommended area of steel and then input it afterwards. So after defining the data for D4, so we can copy these reinforcements to both of the other composite sections. So, and then close this one. Now, after we defined everything, there are other loads that I haven't included in this tutorial, like the thermal effects as well as the earthquake loads. So maybe we can include it in some other time. So I will be running the analysis for this model. So let's go to the analysis tab and then click on perform analysis. So the runtime of the analysis is purely dependent on the complexity of your model as well as the specifications of the hardware that you are using. Also, if there are other applications that are open with with MIDAS. So let's wait after this analysis is performed. We have finally finished the analysis for this model. So as you can see, the analysis is conducted after 850 seconds. Now when we go to the results tab, you can see the load combination function. You can click on load combination and then let's make use of the auto generation button. Then for the code selection, use the concrete option and then look for the Australian code. And then for us, we will include the static load cases and the construction stages load cases. And then for the bridge type, let's use the roadway bridge type. And then there are two types of load factor. One that reduces safety and the other one increases safety for the bridge. So let's click on both. And then if your load combination for the moving load needs to have fatigue, or if the moving load that you have applied on your model is under fatigue load, you can define this as such. So since we don't have fatigue load combination, let's just click on OK. And then you can see here the load combinations that are applicable for our model. So this load combination should be copied into the concrete design. So when we go to the concrete design tab, you can see here that the load combination for strength are added already. So you can choose here either strength load combination or service load combination. Then choose this one. Then here are some of the results that are applicable or that can be applied to our model. So first one is the reaction. So say for example, for the first load combination, and click for the reaction there, and get the values. So you can also choose if you want to see only the minimum or the maximum values of your reaction. So here are the minimum and maximum values. And then deformation, you can also see the deformation contour. This is the deformation due to the combination 1. You can also change the scale of the displacement contours if you want to. And then for the beam diagrams, or you can see it here. So here are from different types of the beam diagram. So for the envelope load combination. And you can also see the 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 loads for the moving loads that will produce either minimum or maximum in this particular key element for this particular load case. So if you want to see the maximum, the critical moving load, sorry, let me repeat it. So moving tracer gives you the load conditions that will produce the maximum of this of fx, fy, fc, and mx, my, or nz. So either of these components you can choose if you want to get the maximum value of those due to a certain element. So for example, if you want to see the maximum moment about y that will be produced about key element 401 or 517, and click on apply. And then as you can see, this will be the loading condition that will produce the maximum moment on this particular element. So you can apply it as a static load in your model by clicking write min-max load file. Then you can check if you want to add additional centrifugal force and then additional longitudinal force for your model. Then click on OK. It will then produce a text file. So here's the text file, which you can add to your model afterwards. So let's just um, we will need to copy everything and then go to the Tools tab, then use the MCT command shell and then copy it and then run it afterwards. So that's what you need to do if you want to include this particular load combination with the centrifugal force and the longitudinal forces. So I will not do that since we need to move on to the design part. I'll just close this one. We can also see the tendon losses in our particular model. So you can click on tendon loss graph, then click whichever tendon you want to see. Then this will be the tendon loss graph for the span 1 first tendon on stage 1 to 5. You can also see other tendons. Then you can also see it as in table form. So all of this data here can be seen as a table form in the results table tab. So say for example, tendon, if you want to see the tendon losses, so results, so you can choose whichever tendon you want to inspect, either in span 1, span 2, or span 3. And then this would be the data that would be available. So you have the instantaneous losses, and then the relaxation loss, and then the long-term effects. So you can see it by stress or by forces, whichever is efficient for you. Let's close this window. Then let's go now to the design part. So we would be using the PSC tab for the design. Let's choose first the code that we will use. So we will be using AS5100 and then define the parameters. So first would be the size of your maximum nominal aggregate and then the maximum increment of steel stress for the crack control checking. So these options are for output or the results that you can see afterwards. So these are the things that would be included in the Excel report of the PSC design. So need to check it all. Then click on OK. You also need to define the PSC design material. So we have two material for concrete design, C50 and then C40. We need to define both of that. So for the rebar selection, let's look under AS17, then choose D500L. Then for the slab, let's use AS17, then C40. Rebar selection is also under AS. So D500, then modify. Let's do it again for C40. So C40, Girder is C50. Rebar selection is from AS17 as well. Grade of the main rebar and the sub rebar. Also need to define the stab. And as well as for the rebar selection again, let's input the grade of the main rebar and the sub rebar. Modify. Close. Then for the design and output position, so for the design position, you need to select the elements which you want to have a design output. So if you want to design, for example, this um, let's let's activate only this part and then say for example we'll be designing the first girders. Click on apply. So all of these girders will have a design output. And then for the output position, we'll just say for example try this one. This will have a report in Excel. So for us to run the analysis or the report, the design faster, I'll just only pick 3 elements. Let's add 3 more. And then for the exposure class, um, so here is the exposure classification for ES. So the members are protected by damp-proof membrane in non-aggressive soil should be A. And for note 4, here's the note 4 for B. And then for U exposure classification for in aggressive soils. So you have A, B1, B2, C1, C2, and then U. So if you haven't defined this, it will automatically have an exposure class of A. So let us now perform the design. Now that the design part of PSC has been completed, we can see the results here in the results table. So we have results for lecture. So you can see here if there are members that did not pass the requirements. Same with shear. Sorry. And then combine shear and torsion strength. You can also see the values in a diagram form. So say for example, if you want to see all load combinations and with the force, and if you want to check the flexure about Y, yeah, so here's the diagram for the flexure about Y, and this is the diagram for the shear. As you can see, we can only extract the diagram for the girders that we assigned design option to. And then for the torsion, here's the diagram. You can also include safety factors, say for example 0.75. So here are the girders that pass the 0.75 criteria line. And you can also extract the Excel report or the detailed calculation of PSC design based on AS5100.5 in the Excel report. Just click on Excel report. And then it will generate the report as such. So here is the spreadsheet for all of the members that we assigned output for into. So we have member number 138. So you can see here the code that is used, the section properties, the materials, then the pre-stressing steel information, the longitudinal steel reinforcement that we input using the section manager, sectional forces due to effective pre-stress. Then here's the flexure design for this section. Flexural resistance, computation, and then the results. The shear design for the section. And for the shear reinforcement design as well. Torsional design is also here. So I sent you a copy of this spreadsheet for you to be able to check the data that was extracted automatically using the PSC design according to AS5100. So that would be it for the Super T Girder bridge modeling, analysis, and design as per AS5100, point 2 and then point 5. So thank you very much for listening to our webinar. We hope that you continue attending our webinars and don't forget to, to look for the follow-up emails after this webinar. Yeah. Thank you very much and always keep safe. Bye. If you have any questions, just email us at phinquiry@midasid.com. Thank you.